Yeah. Okay. So I will make a focus on neuromorphic sensors for defense. First, I will try to introduce Thales very rapidly. Thales is a company of about 80,000 employees in 68 countries, and we are investing in R&D 4 billion per year. And we have a revenue around 19 billion. So it's a rather big company, and the goal of the company is really to empower the customers to face decisive moments with confidence. That's where these neuromorphic sensors are come into place. Because the first things that we have to do to take this decision is to detect and register some data in order to take the right decision. And that we will see that these neuromorphic sensors can bring some added value for that. We'll see that in the near future. In Thales, which is a rather big company, I'm in a business line called Optronics and Missile Electronics. And in this Optronics, because I'm mainly on the Optronics side, we are now doing different applications. We are doing equipment for defense, which could be for land, for airborne, or for naval applications. Here you see, for example, a pod, a targeting pod, which is very largely developed and sell. It's our fifth generation of pods that we are producing for quite a long time. We are also doing scientific lasers, and that you see here on the second picture. And we have this missile for the guidance of missile, obviously, but we have also these cinema zoom applications that we are addressing. So we are not only defense, but we are also addressing some science and civilian applications. Just to go fast, we are this business line footprint is not in France only. We have a lot of people in France, but we have also some large development center in the UK, especially in Scotland, in Glasgow, and we have also some activities in making cryogenic coolers in Eindhoven and in Blagnac, near Toulouse in France. And we have some developments of camera, mainly based on uncooled sensors in Canada. Okay, so here I introduced you that we are in the Thales Optronics and Missile Electronic business line. We are addressing mainly all the type of defense applications, land, airborne, and naval, and we identified a lot of applications on which the neuromorphic technology could be very interesting. And it's really what I want to present to you today. Some of the outputs that I will present today are coming from an EDA program, an OB study called NEDA, to which we participate. And I see that Nicolo will also add some information on that, because we worked with FlySight for this one. We work with FlightSight, with Marduk, the University of Luxembourg, and SALT also. We're part of this large consortium, and together, the 5 partners, we identified several advantages of this technology for our defense applications. The first main interesting characteristics is really the high temporal resolutions, which allows you to capture fast-moving objects, for example, and to obtain a greater detail in the evolution of the motions without having to interpolate between the different frames, as it's the case with a normal and traditional technology to capture images. And so it could be very efficient if you want to apply some tracking algorithms, for example. And it also has a low latency, that means that these neuromorphic sensors can respond very quickly to any change in the environment and allows you to take a very fast decision, which is sometimes very, very critical for defense application. Also, an interesting characteristic is the high dynamic range. So you can, if you have in the same image, capture some bright objects, a bright part of the scene, and also dark elements of the scene without losing any detail. This is very interesting, especially in several type of applications. For example, if you imagine that you have a large field of view, very large field of view, if you want to make to protect, for example, the platform on a 360, you would have some parts which are in the bright part illuminated by the sun, and you would have some shadow for some other parts, and to have this automatic adjustment of the dynamic. Because the dynamic is really very large for this kind of sensors, pixel per pixel, so it's very an advantage. Yes, it's low power. It consumes less energy than a traditional camera, so it's a very benefit, especially if you want to address soldier applications, for example, where the soldier cannot bring with him a lot of energy, because energy means weight in that case. And if you want to, they are very supporting large weights, and so to have a low power means less weight and more informations that you can, let's say, capture per kilo. And the data sparsity, it's very an advantage, and especially when you process the data which are at the output of the sensor. Yeah, you only capture what is changing in the scene, and so in a lot of situations, what you capture, what is changing in the scene, is a very limited number of pixels in comparison to the whole frame. Even if you are moving, if you, for example, you imagine that you put your neuromorphic sensors on the moving platform. A lot of the part of the image are very uniform in terms of illuminations, and they won't detect, they won't generate any change in the image from frame to frame. So this kind of situation, a neuromorphic camera is very interesting. So in the data project that we discussed and we introduced just before, some applications has been identified. This has already been published by EDA. All those results belongs to EDA, but I took some results that I have published on their site from their own innovation forum. So that's why I take the liberty to repeat what they just published. Detection and tracking, including trajectory determination of fast-moving objects. It's really an application on which you can benefit a lot of this type of technology. For example, if you want to consider high-velocity missiles, hypersonic missiles, for example, or bullets in projectile warning systems, swarms of UAV, where you have a lot of different UAV in the field of view, flying in front of you. If you can have only track all of them all together without having a very complex processing, it's very interesting. The detection of UAV in counter UAV system. I just repeat what we just said before, but mainly, yeah, if you have a very complex environment, if you can detect only what is changing, even if what we call a strong background, very complex background, it's very interesting. Especially the large dynamic range allows you to even detect this UAV in front of the sun, for example, and this is very interesting. Situation awareness, behavior detection, recognition of threats, assessment, alert generation. Okay, it's another interesting application. Obviously, all the autonomous systems where you can benefit of the data sparsity, the high dynamic range. For example, high dynamic range constraints like entering or leaving a tunnel. It's something which is And as we will see later on, it's an application that we addressed before this NEDA project, is the laser warning systems, because you can use this technology also to detect these lasers in laser warning systems. Okay, well, is it moving? Yeah. So just here, some image we captured of a UNAV in front of a complex background. We did that with several cameras in parallel, and one of the camera was an event-based sensor, a neuromorphic sensor, and this one was used for the tracking of the objects. Oh, where is it? Okay. For example, here, I hope you see well, but you see we had a very complex background. We just have a UAV which is not at a long distance. Obviously, it's not a long distance here, but you can clearly see this one. You can clearly see that it's a UAV. You can clearly identify the type of UAV it is, and so it's much easier to track for the algorithms than in a traditional image. You have not a lot of information. It's black and white information, but it's good enough for the tracking operations. Okay, and another application that I want to show you, it's a laser pulse detection application. We can use this type of technology for that. A lot of applications requires the asynchronous detection of laser pulses, and this can be done with an event-based sensors. I must say a few words here on the wavelengths. If you do a neuromorphic sensor in the visible, it won't be so much interesting, because most of the lasers that we use in defense are in the near infrared range, around 1550 nanometers. And but we made some experiments in the visible by using a prophecy sensor, just to see if we could do something with this kind of technology and if it's interesting. So what we have done is to tune the sensor outside the normal domain of this sensor. But it led, obviously, because it was not working, it was not designed to work in this way. We had an important increase of power consumption for the sensor. Anyway, we were able to make some testings that I want to show you now. Obviously, it's not the only way to design a sensor with this asynchronous laser pulse detection function, because we have on the market some other sensors in the sphere which are doing that. But I would like to show you now that this kind of neuromorphic sensor can be used also for that. So here what we have done is to use a Gulf rangefinder, which is in the visible range, which is not in 1550. And you see here, with the normal settings of the sensor, you see that this guy who's having this rangefinder in hand, yes, you can see this pulse, but you have also a lot of parasitic information which are coming from each type is moving anyway, and things. What we have done afterwards was to change a little bit the settings. How can it goes? Doesn't move. Okay, no, yes. We change the settings in order to keep only the information coming from the laser. So if I now show you the video, it's very poor in terms of information. You just see the laser pulse here, and any other things which were moving in the scene, like the guy who is moving, the cars, the gate which is opening and closing, everything disappear because they are at low frequency. And so you can tune your sensor in order to keep only what is changing fast in the image, and not the low frequency evolutions. And in that way, you can keep only this laser pulse information, which is the case when you are when you have this normal ALPD function in a sensor, and you can harmonize your sensor with any other one in order to have the complete information of the context plus this detection. So it is working quite interestingly. So that's it for my presentation. I just wanted to show you some of examples of applications in the defense domain. We think that there is a large benefit of this technology for our applications. That's why we are trying to continue to work around that, trying to see if we can have disposite of an event-based sensor in the infrared domain. We know that in US there were some programs around that also. There is some work done in the UK, some work done in Israel also on that. And so among Europe, several actors are interested in this technology. And we are trying to pursue on that. Thank you very much. And I give you my contact if you want to contact me after the presentation, because I know that it's not so easy to exchange during such presentations. Thank you very much.